So today class we are discussing about the a simply supported beam and a UDL entire length Therefore, the UDL value is small w. The UDL value is small w, and I need to find out the reaction forces at RA and RB. I need to find out the reaction forces at RA and RB. Therefore, I need to convert the UDL into point load whose magnitude will be small w into L. And the point load will be acting at the center of the span. Therefore, it is a point load at the center. Therefore, RA is also equal to RB, which is equal to W, capital W by 2, where capital W is small w into L by 2. Therefore, the RA value and RB value is small w L by 2. Now considering a section of XX at a distance of small x from the B point. So therefore, we have two forces. First force is RB, and the second force is a converted UDL whose magnitude is small w into x. And we have a distance of x from the section, and we have a distance of x by 2 from the section. Therefore, I will get RB into x. Is a moment, and it is a positive because the moment is anti-clockwise direction. This moment is anti-clockwise direction. And another force is capital W, and its distance is x by 2, where capital W is small w into x, and the distance is x by 2. Therefore, I am attaining small w x square by 2, and it is a negative since the load is moving the beam in clockwise. Therefore, we have proved that mx is equal to ei d square y by dx square. Therefore, substituting instead of mx, ei d square y by dx square is equal to small w L into x by 2 minus small w x square by 2. This is the first equation. Now integrating the first equation with x. So integrating the first equation, we will get dy by dx, and integrating of x, we will get x square by 2. Therefore, 2 into 2 will get a 4. And next, integral of x square. So we will get x cube by 3. Therefore, 2 into 3 will get a 6 w x cube. This is cube x cube by 6, and plus a integral constant as c1. Now I need to find out the integral constant for a simply supported beam C1 by applying the boundary condition. Therefore, the boundary conditions are b at x is equal to L by 2, dy by dx is equal to 0. Therefore, substituting in my equation 2 to find the C1 value, x is equal to L by 2, and dy by dx is equal to 0. dy by dx is equal to 0. Therefore, we are attaining a value of C1 as small w L cube by 24 a negative. Therefore, substituting the C1 value in the equation 2, substituting the C1 value in the equation 2. Now, I need to find out the slope at a B and at a C. That is nothing but, if I consider a simply supported beam, there will be a slope at A and at B. So I need to find out the dy by dx at A, and it is also equal to dy by dx at B. Therefore, substituting x is equal to 0, we can find the dy by dx. Therefore, it is nothing but w L cube by 24. Substituting x is equal to 0, this becomes 0 and this becomes 0. Therefore, this is C1 value, this is C1 value. Therefore, the only value remaining is minus w L cube by 24. Therefore, the slope at B is w L cube by 24 EI. Now, again integrating the above equation, we will get EI y is equal to small w L cube x cube by 12 minus small w x to the power of 4 by 24 and minus w L cube by x by 24 plus C2 an integral constant. C2. So to find the integral constant of C2, I am applying a boundary condition, that is at x is equal to 0, y will be equal to 0. Since at B we are getting the support, therefore there will not be any deflection at the support. Therefore, y is equal to 0. At the support. Therefore, substituting the values b is equal to 0 and x is equal to 0 and y is equal to 0. Therefore, we will get an equation C2 is equal to 0. Substituting x is equal to 0 and y is equal to 0 in my previous equation. That is a deflection equation. Now, again rewriting the equation C2 as 0, and this is the final equation. Of a deflection at any point. So if I consider a simply supported beam and a UDL on length of the beam, therefore a deflection, I need to find out the deflection at any point. So to attaining it, the same formula need to be used while substituting x is equal to 0, x is equal to 1, x is equal to 2, and so on, x is equal to L. So we can find the deflection at any point. So the deflection here is maximum at the center, since if I converted this UDL into a point load, it is acting at the center. Therefore, the deflection will be maximum at the center of the beam. Therefore, substituting x is equal to L by 2, we will get y max. Substituting x is equal to L by 2, we will get the y max. Therefore, substituting the x is equal to L by 2 in my y equation. Therefore, I will get a y max. Y max is equal to 5 into WL to the power of 4 by 384 EI. So minus represents the deflection is in downwards direction. So next problem is a cantilever beam. Next problem is a cantilever beam. A point load is acting at the free end. A point load is acting at the free end. Therefore, we do not require RA and MA values. RA and MA values. We do not require RA and MA values. So here I need to find out the section. I need to consider a section. I need to consider a section at a distance of small x from the free end. From the free end. Therefore, the bending moment at xx is equal to the bending moment at xx is equal to W into distance is x, and due to this load, the movement is in clockwise direction. The movement is in clockwise direction, so it is a negative. We have proved that EI d square y by dx here is equal to m. Therefore, rewriting the equation, this becomes the first equation. Next, integrating the both sides, we will get dy by dx, and integrating of x, we will get x square by 2, and an integral constant of c1. Now applying the boundary condition for a cantilever beam. So for a cantilever beam at x is equal to L, that is dy by dx is equal to 0. That is nothing but at a fixed end. At the fixed end, dy by dx is equal to 0. That is nothing but a slope is equal to 0 at the fixed end. Therefore, substituting x is equal to L and dy by dx is equal to 0. Therefore, C1 is equal to WL square by 2. Again, substituting in my previous equation 2, so I can rewrite the equation EI dy by dx is equal to minus WX square by 2 plus WL square by 2. Now, I need to find out the deflection. Therefore, again integrating the above equation 3. Therefore, we will get WX cube by 6 plus EWL square by 2 into X plus C2, an integral constant. This is the deflection equation at any point for a cantilever beam. This is a deflection equation for any point for a cantilever beam. So here it is a cantilever beam and a point load is acting and the beam will be deflected. So I can find the deflection by varying the x, that is nothing but section. I can find the deflection at that section. That is substituting x is equal to 0, x is equal to 1, x is equal to 2, x is equal to so on, and x is equal to L. So I need to find out the deflection for substituting x is equal to 1, x is equal to 2, x is equal to 3, and so on. And at the fixed end, the deflection is 0 at L it is 0. And if you see the diagram, we are observing the maximum deflection at the free end. The maximum deflection is occurred at the free end. Therefore, x is equal to 0. At x is equal to 0, the y becomes y max. Y becomes y max. Therefore, substituting the x is equal to 0 in my standard equation, therefore I can find the y max. So here C2 is a constant again. C2 can be found by applying the boundary conditions, that is at the fixed end. At the fixed end, the y is equal to 0. That is, we have a support or a support. Therefore, at the support, the deflection is 0. Therefore, applying that, I can find the C2 value, and substituting the equation, I will get the maximum deflection under the cantilever beam when a point load is acting at the free end. Next derivation is a cantilever beam when a load is acting at a eccentric, that is some length, not at a free end. So to derive this derivation, I need to consider only AC length. I need to consider only the AC length. So now this is AC and a point load at the C point, and the length in between A and C is L1. Therefore, I can find the deflection, the maximum deflection at the C. I can find the maximum deflection at the C, that is YC, which is a known value, that is nothing but W L Q by 3EI. So we here L is nothing but L1. Therefore, W L1 cube by 3I is the deflection. At the C point. Now, if I consider in between C and B, it is a straight line. Therefore, it has this same slope. So, if I consider a straight line, we can have a slope equal at any point. We will have a slope equal at any point if it is a straight line. So in between C and B, it is a straight line. Therefore, the slope at a C and the slope at a B are equal. The slope at a C and the slope at a B are equal. Therefore, we can find the slope at a C, that is W L1 square by 2EI, which is also equal to the slope at a B. Now, I need to consider this as a rectangular and a triangle. So the rectangular whose width is YC, and we need to find out the unknown depth. This value from here to here. Therefore, YB is equal to YC plus some unknown value of Y. Therefore, I need to find out the Y. So here a triangle is observed. Whose length is L minus L1 and whose opposite side of that angle, this is the angle, this is the theta, and opposite side is Y. Therefore, I need to find out the Y. Therefore, tan theta is equal to Y divided by L minus L1. Therefore, theta at C is equal to into L into L1 is equal to Y. Therefore, I can substitute the value this as a C into L minus L1 is the deflection at the free end. It is the deflection at the free end. Therefore, we can find the deflection at the free end by considering a small region, that is BC as a straight line. BC as a straight line. With this, I am concluding, Amma.